Hello everybody, welcome to the first lecture about foundations of geometry online. I hope you're all staying well and healthy. This is definitely not my preferred mode of teaching, but we have to do with whatever we have. As you see, I don't have a blackboard, but only this whiteboard, and I don't have the colored chalk, but I have this. So lots of colors here, and we'll use that instead. However, as you probably have figured out by now, by watching me teach in class, I don't actually know what to do with color chalk. I just put the colors kind of randomly on the board so that the picture looks colorful, and I can promise you I'll continue this tendency here. So the first lecture is not going to be about new material, but rather I decided it's a good idea to review what we had done in class in the past week. So we talked about inversions, so let me just review some basics about inversions in this video. So the title, as you see, is a review of basics about inversions, and first I begin with a definition of what it means for 2 points to be symmetrical with respect to a circle. So we give ourselves a point C, this one here, on the plane, and a circle. That's not the same type of C, right? That's a calligraphic C. The radius of the circle, calligraphic C, is K. And then we say that 2 points, P and P prime, are symmetrical with respect to K if two things are true. Namely, actually, let's start with the second thing here, that if I draw a line through, so if I connect C, P, and P prime, these 3 points are actually collinear. So if somebody asks you to construct a symmetrical point with respect to some circle and gives you a point P, you know that the image of that the symmetrical point is going to lie on the same line as the line going through C and P. So C, P, and P prime are collinear, and C is outside of the line segment P, P prime. In other words, you have a ray, you draw a ray from C through P and continuing in that direction, and you know that the symmetrical point P prime is going to lie on that ray. Where exactly on this ray P prime will lie is given by this condition here, that if I take the distance between C and P and multiply it by the distance between C and P prime, you get exactly a radius square. This can be sort of nicely rephrased by saying that the radius is the geometric mean between these two distances. However, the upshot is that one thing to observe is that if I move this point P closer to the center, then because of this equality, the other point moves further away. On the other hand, if I move the point P closer towards the circle, P prime also moves towards the circle. And if P lies on the circle, then it's actually equal to P prime. On the other hand, if P, of course, starts life outside of the circle on that ray, then P prime is inside the circle. So with this, we can now define what an inversion is. So let C and K be a point and a positive number, respectively. Define a map I, C, comma, K this map, which is called the inversion, with respect to the point C and of radius K, is a map that's defined on every point of the plane except for the point C. And how do we define it? Define the map such that if I take any point P, then I get P prime, where P and P prime are symmetrical. With respect to, that's just my little abbreviation for with respect to the circle calligraphic C centered at C of radius K. So some properties of this map are the following. Some properties. Of ICK. One, it's a bijection. Two, it is its own inverse. Yes, if I apply the same inversion to any point, I get the same point back. Three, it fixes only exactly the points that lie on the circle. So a point is fixed if and only if its distance from C is equal to K. So these are some basic properties of inversions, and we spent maybe the last two lectures trying to understand where inversion maps various geometric objects, in particular lines and circles. However, before I get to this, let me come back to this picture here, picture that we're going to actually be using in a lot of the things that we're going to be doing with inversions. There are not so many things we're going to be doing with inversions, just to calm you down. But in any case, this picture is actually useful. So this picture tells you how to construct a symmetrical point from a given point. In other words, how to construct the image of any given point under the inversion. So if you want to construct the image of P under the inversion, what do? Well, first of all, you connect the point C with P with a ray, and you know that P prime is going to be on that ray. Secondly, you draw the circle calligraphic C. You see, the circle is not really part of the data that defines the inversion. It's just the point C and the radius. But if you have a point and you have a radius, then you also have a circle. So you know how to draw that circle calligraphic C. It's a circle centered at C of radius K. And you have that point P here, and then you draw a perpendicular line segment to this ray going through P. So this perpendicular line segment is going to intersect the circle at some point, and then you draw a tangent line to the circle at that point. And this tangent line is going to intersect this point, this ray at some point, and that point is P prime, which is the image of P under the inversion. You can also do this backwards. If I have a point P, if I start with a point P prime that lies outside of the circle, I can just draw a line that goes through that point and is tangent to the circle, connect these two by a line, and then draw this perpendicular that goes through that point, and this gives me the point P. So this construction works well both ways. Okay, so let's now state the theorem that we spent the last class or two proving. And I will not reprove it, but I will just discuss various parts of it, and we'll do a few examples of how to construct images of lines and circles. So our theorem was the following. So let, again, C be a point. and k be a number greater than 0, then the inversion centered at C of radius k maps. Okay, there are 4 cases. One, lines through C to themselves. Two, lines not containing C. So lines not through C. To circles through C. Three, circles through C. To lines not through C. And finally, circles not through C to circles not through C. So let's now do a few examples of these things. So for the case 1, for examples. So I'm going to start with giving myself a circle. I call it the circle of inversion. That is, the inversion gives me a point and a radius. So if I draw a circle centered at that point of that radius, I'll call this the circle of inversion. So okay, so this is the circle of inversion. You see the radius being k. So first, let's start with a very easy case, namely the case number 1. If I draw a line that goes through C, then in that case, what will the inversion do to this line? Well, if I take any point on this line, let's say this point here, and I apply the inversion to it, it's going to map this point to some other point on that line. So it's really clear in the case number 1 that this entire line is going to be mapped back to itself, because any point on this line is going to be mapped to a point on this line. So that's really the easiest case. Okay, so here's another circle of inversion. The radius is still k. And now we're going to take a line outside of the circle. So some line M. And so how do we get, so according to part 2, it's the part 2 of the theorem says that this line should be mapped to a circle, and that circle would not go, the circle will go through C. So these I know something about that circle already. I know that the circle passes through C. So we discussed this in class during the proof of that part, how to actually find the circle, the circle exactly. So first we draw a perpendicular line that goes through C and is perpendicular to this line M. So the point of intersection, let's denote it by H. And now I would like to find the image of H under this inversion. So what do? I essentially just use this method I described to you a moment ago. So I take this point and try to draw a tangent line to the circle. Okay. So this is a line that's tangent to the circle, and then I draw a perpendicular line, and this here is H prime. So this H prime is by the definition the image under the inversion of H. And now the proof of the theorem told us how then we can get the image of this line M, and I'm going to also draw it in red for you to see that this is actually the image of M. So the theorem, or the proof of the theorem, told us that this line segment CH prime is actually now the diameter of the circle that is the image of M. So that circle here is the image of M. So the line M is mapped onto that circle. So let's try to repeat this construction, but now let's move the line a little bit closer to the center so that it actually intersects the circle of inversion. In fact, if you wish to practice this, you can try to do this yourselves and just pause the video, and I will do this now. So again, we start with a point and a circle. Maybe it's easier to first draw the circle and then decide where the center is. Somewhere here. It's not really nice. Okay, so this is the circle of inversion. And now I take a line M that will go through the circle, but still not through C, right? These are still lines that do not go through C. So just like the other time, let me actually move this C a little bit. I first draw a perpendicular line to this, and I call this H. And my first task is to find the image of H under the inversion. So I again use the same trick, namely use this perpendicular, draw a tangent line, and this gives me a point H prime. Actually, let's write this H prime here. So H prime, as before, is the image of H under the inversion. Okay, and now you already know what the image of that line M will be. It will be just that circle whose diameter is going to be CH prime. Well, let's see if I can draw that. Okay, it doesn't really look very much like a circle, but you know this already from class, that's how I draw circles. One reason also why I wanted I was willing to sacrifice the shape of it to stress one thing, namely, I know, right, that these points here, the points where the line intersects the circle, so they lie on the circle, so the inversion must map these points to themselves. Therefore, the circle, the image of the line must intersect the circle of inversion in the same point as the line intersects it. So that's kind of sort of a guiding principle for you to connect these two. So the circle must go through these. Okay, let me pause here, and in the next part we'll see how to get part 4.